In this video, we're going to address three questions about acid and base strength. What are strong acids and bases? What makes an acid or a base strong? And how is it that you can predict which side of an equation is favored in an acid-base equilibrium process? So the strong acids are these seven. Memorize them. An acid is strong if its conjugate base is stable. This means that an acid is strong if it's good at donating H+. So for example, if you put HCl in water, you will find that it completely ionizes. It goes 100% to H3O plus and Cl minus when added to water. And that's because this conjugate base of Cl minus is very stable. Now, you might recall that chlorine is very electronegative, and as a result, it can hold a negative charge quite well, quite easily, and that's one of the reasons why Cl minus is such a stable conjugate base. By contrast, H2S is not one of the seven strong acids, and so it is a weak acid. And it's weak because the HS minus anion as a conjugate base is not very stable, and you can say that has something to do with the fact that sulfur is not quite as good at holding that negative charge because it's not as electronegative as, say, chlorine. There's a little bit more to it than electronegativity, but that's a good starting point. Next, we'll talk about strong bases. They are the group 1 and 2 metal hydroxides, sodium hydroxide, potassium hydroxide, barium hydroxide, calcium hydroxide, and so on. What makes a base strong is its conjugate acid being stable. In other words, a base is really good at accepting an H plus and not losing it again. So for example, OH minus is a very strong base, and that's because the conjugate acid H2O, when we've added an H plus to it, is very stable. This is not very acidic, and so it is very stable. The hydroxide is a good H plus acceptor. Now, Cl minus is a very weak base, and it's a weak base because the conjugate acid, HCl, is not stable. As we've discussed before, this is really good at losing the H+, so it will, and it'll go straight to that weak conjugate base, Cl minus. So in an equilibrium process, the equilibrium will favor the side with a weaker acid and base. So if we look at HCl and OH minus, this is a strong acid, one of the seven. OH minus we're going to call a strong base. And at equilibrium with water, well, water is going to be a very weak acid. Chloride, as we've discussed extensively, is a weak base. So this reaction isn't really even at equilibrium. Pretty much 100% goes towards the right side. If we talk about HCl, again, a strong acid, and Cn minus, this is a weak base, giving us HCN, which is a weak acid, and Cl minus, which is a weak base. This is still going to go pretty much 100% to the right. Strong and weak gives us weak and weak. Overall, the right side is weaker, and this side will be favored. Similarly, a strong base and a weak acid giving us a weak acid and a weak base, we see that the right side is going to be favored almost to 100% again. Now, what if we have HNO2, which is not one of our seven strong acids, this is a weak acid, and F minus, which is a weak base, giving us the conjugate base that is a weak base, NO2 minus, and a weak conjugate acid. What about that? Well, in this case, we're going to have to go to this chart right here. And we can just compare the two acids. We had nitrous acid, HNO2, and we also had hydrofluoric acid, HF. And what we can see is that higher on this chart means stronger acid. And we can see that the Ka of HF is bigger than the Ka of nitrous acid. So I can say that HF is not a strong acid, but it's stronger. And I can say this is a stronger acid. The HNO2 is the weaker base. And actually, the conjugates bases kind of fall in line with that. The NO2 minus is going to be a weaker base, or rather a stronger base, excuse me. and the F minus is going to be a weaker base. And I can tell this based on the fact that F minus lines up actually right next to HF, and NO2 minus lines up right next to HNO2, but the lower you are here on this side, the stronger the conjugate base. Notice that my Kb is higher here for NO2 minus than the Kb for F minus. And actually, you can use this chart. What you might notice is that you'll have on the left side an acid, and on the right side will be its conjugate base. And so, for example, with hydronium and water, they are conjugates. You might find that the Ka and the Kb for the conjugate base, when you multiply them, they give you the Kw of 10 to the negative 14. In this case, it's easy to see. 1 times 1.0 times 10 to the negative 14 is 1.0 times 10 to the negative 14th. That is the Kw. But you would also find that to be the case in the case of HF and F minus. Multiply the Ka of HF and the Kb of F minus, and you will get 1.0 times 10 to the negative 14th, the water constant. Any differences are just a result of rounding and sig figs. Finally, I just want to point out that we've already decided that this equilibrium favors the left side because we have weaker on this side and we have stronger on this side. Well, what that means is that at equilibrium we're going to have more HNO2 and F minus. That means that, well, you're going to have some NO2 minus and some HF, and I've drawn that in this beaker right here. If you count them, we still have, say, 3 of each, but it's just that there's going to be more of the HNO2 and there's going to be more of the F minus. I've demonstrated that by drawing 5 of each. So I hope this video has been helpful. Feel free to leave any questions or comments in the comments section below. Thanks for watching.